Okay, so just a couple other concepts to kind of wrap up the voltaic cell part before we move into the electrolytic cells. One of those things is cell notation. So cell notation is a shorthand way to represent a voltaic cell. What happens in cell notation is we really only show you what is participating in the reaction. We leave all the spectators out. So here's an example right here of what that looks like. So you'll notice a couple of things. You'll notice that we have these double lines. So this double line means the separation between those two containers. Okay, so that double line is the split between the cells, right? So that's already here. The double line represents the porous barrier or salt bridge between the half cells. Okay, the single lines that we also have, those just basically mean that there's a phase boundary, right? So there's a difference in state between them. So because we have solids and we have aqueous, we use that single line to separate them. Okay, you would find if we had like a solid, aqueous, and a gas, we would also use an additional solid line to be able to separate that as well. So double line to represent that boundary between the two separate half cells, and single lines to represent that change in phase. So the other thing you're going to find is we generally tend to work in from both sides. So you'll notice that we have the solid, or our electrodes, that are on the outside. Okay, that's always how it's going to be. You're going to have the solids, and then you're going to work your way into what those solutions are. Okay, so typically the anode is shown on the left-hand side and the cathode on the right-hand side. However, just because that's the convention doesn't mean that's the way it's always going to be written, okay? You will find on like old diploma questions, sometimes it's written that way, sometimes it's written the other way. It kind of goes both ways, and that's because they really want to check to see, do you actually know how to find the SOA and the SRA? Or have you just memorized anode on the left, cathode on the right? So some pictures do absolutely follow that convention, but you will find that there are some that do not follow that convention, okay? So here's a quick example of a cell and what that cell notation looks like. So you can see here we have Pb solid, Pb2+. So that's basically telling us that our half reaction is either the Pb solid turning into the Pb2+, or it's the Pb2+ turning into Pb solid. Then over here in our other beaker, it says iron 3, iron 2, and platinum. So you'll notice that inside of this beaker, we actually have two solutions. And that's because we have this one giving us the iron 3, and we have this one giving us the iron 2. The other thing you'll notice is what our electrode is. It's PT solid, right? Some of you might be wondering, why aren't we using iron, right? Iron would work in this case, so why aren't we using that? So the reason we're not using iron in this case is, if you think about it, if I put an iron strip into an iron 2 solution and an iron 3 solution, those will actually react with itself. And we don't want that. We never want to have a spontaneous reaction within one of our containers, because as soon as that happens, there's going to be no flow of electrons through the wire, because they're just going to flow within this beaker directly from one thing to another. So this leads us into the next concept, which is talking about what we call an inert electrode. So an inert electrode is an electrode, because we always need electrodes, right? We can't not have electrodes. We need a surface for electron exchange to occur. But inert means it doesn't participate in the reaction. So in this case, this is a perfect example of where I need an inert electrode. I can't use an iron electrode because it will actually react with itself. Okay, other situations where I would need an inert electrode would be if my half reaction doesn't involve a solid metal. Okay, so far everything we've kind of looked at and all the examples you would have seen if you worked through your booklet, they've almost all been like, I don't know, zinc solid in a zinc solution, copper solid in a copper solution. But when you start looking at your data booklet at all of those different half reactions that are in there, like some of them involve solid metals. And so then it's easy for me to be like, oh, well, I want to do the aluminum half reaction. I could use aluminum. But what if I'm using something that doesn't involve a solid metal? So let's say, I don't know, I want the water half reaction to happen, which is right here, 2H2O liquid plus 2 electrons to give me H2 gas and 2 OH minus. I don't have a solid metal in that equation that I could use to be my electrode. So that's another situation where you find you need an inert electrode, is when there is no solid metal inside of that actual half reaction that you are using. So for the most part, when we are using inert electrodes, we kind of have two that we generally tend to use. One is platinum, and the other one is carbon in the form of a graphite rod. So platinum is an inert electrode. You'll find that platinum isn't in your data booklet as either an OA or an RA, and that's because it's so weak that it's off the chart. So it's a safe thing to use as an inert electrode. When I'm choosing something to be an inert electrode, I have to make sure that I'm choosing something that's actually going to be inert, right? If I choose some metal that's actually quite reactive, I may find that it's not inert. It actually then does start to participate in my reaction. So the one that we tend to use more often at school is going to be the graphite rod. Main reason for that, it costs a lot less to buy a graphite rod than it costs to buy big slabs of platinum, okay? So the graphite rod, you can kind of think of like if you had lead from a pencil, that's really graphite, but just on a larger scale. And we would basically just clamp our little alligator clip to it and then stick that into our solution. So the inert electrode is going to be there to provide a surface for electron exchange. It's not there to actually participate in the reaction. You do find, though, that when you are talking about mass changes, right? Remember when we drew our cell, we talked about mass changes and concentration changes. I should still specify what type of mass change happens to it. Okay, generally what you find is generally the mass of an inert electrode does not change. Okay, you will find though that when we get into electrolytic cells, there are some cases where it will change, okay? And the reason it doesn't change is if you think back again to the last video, I talked about how you would look at your half reaction to determine if the mass increased or decreased. Well, if it's an inert electrode, it shouldn't be anywhere in my half reaction, so the mass should not be changing. Okay, so the exception to this rule would be unless it is an electroplating cell, and we will talk about that in a later video, okay? But generally we find they don't change because we are not producing more of it. All right, so I want to say the rest of these notes talk about I would call them like STS, right? So your science, technology, and society stuff. Because redox is such a heavy unit and there's so much content to cover, and we really only have, I think it was like, we've lost 64% of our time over what we would normally have in class. I will leave those in your notes for you to have a look over if you would like to. But I'm not really going to go through it because there's not really anything in it that I would say that isn't directly in the notes that you can read, okay? So it talks about dry cells, which are really what you guys think of as batteries, right? When you think of batteries, you don't picture one of these, right? That's not what you think of as a battery. You think of like a Duracell battery, maybe like a little mini like button battery, but you don't picture this, right? Really the only battery you use on a regular basis that kind of looks like this would be your car battery, but again, it's also contained that you don't see any of that, okay? What else does go on? So there's a little YouTube video, can't even remember what it's about, but if you want to watch it, you can definitely take that link out of your notes and just type it in and see what it is. There are some old diploma questions here as well if you want to practice them. Then there's some more STS stuff. It talks a little bit about fuel cells. So fuel cells is a technology that's been around for a very long time. Originally, it was thought to be like, we're going to get rid of using gas in cars and we're going to switch to fuel cells. It's definitely more efficient. The problem is it's not really more cost effective. And the biggest challenge we find with fuel cells is most fuel cells use hydrogen gas as a reactant. We don't have hydrogen gas readily available on Earth. We have to actually fabricate hydrogen gas. And the way we fabricate hydrogen gas is by splitting water molecules. But splitting water molecules requires energy, which in most places our energy is still coming from fossil fuel combustion. So it's one of those where right now fuel cells hasn't really taken off. It may take off one day, but I wouldn't really count on it. Probably see some other type of technology take over. But again, kind of like the dry cells, you should be able to just kind of read through it. It's pretty self-explanatory. Most of the time you're going to find the picture is going to show you what's happening where, right? So here it shows me the anode, here it shows me the cathode. So I know from there the cathode is reduction, the anode is oxidation. I can figure out what my reaction is just by looking at the fact of what goes in and what comes out at different points. Okay, it does go on to talk about a couple of different types of fuel cells. Again, this is all STS stuff. When we get to the end of the unit and we start looking at some of those assessment conversations, we're not going to ask you about fuel cells or dry cells. This is kind of one of those things that you can have a look at if you are wanting a little bit of, I guess I would say, enrichment, even though technically it's not enrichment, it is part of the program of studies. But with the things we've chosen to focus on, we are not going to focus on those, okay?